All right. So we're going to start with the fundamental counting principle. The fundamental counting principle tells you the number of ways that something can be done. So for example, your new phone asks you to set a password that's made of lowercase and uppercase letters. So we know that there's 26 letters in the alphabet. And if we double that, because you have lowercase and uppercase, then you've got 52 separate letters that you could use. And you're not allowed to repeat on this phone. All right, so like if you wanted to put in like Alan, A-L-A-N, you couldn't do that unless you had one capital and one lowercase. You don't want to remember a long password, but you want to feel sure someone else can't guess it quickly. You decide to figure out how many possibilities there are to determine how safe the password is. So let's think about a 2-letter password. For the first letter, how many choices do you have? Yeah, you've got 52 choices for your first letter. All right, and then you've got a second letter. Now, after you choose one letter, say you chose like capital X, that one's gone, so you no longer have 52 choices. How many choices do you have? What do you guys think of Shelby's answer? Does anybody else like 51? Yeah, good. So 52 choices for the first, 51 choices for the second. All right, and let's use a calculator and see how many possible passwords there are. It seems like a lot, and yet computers can hack that in a second. 52 times 51, so I'm getting 2,652. Anybody else getting that? All right, you're gonna have to just trust me then. Okay, so 2,652 passwords, 3 letters. So if I have 3 letters, 1, 2, 3, we know 52 choices for the first, 51 choices for the second, and how many for the third? 50, right? All right, so we're starting to get a bit bigger. Multiply that. Good morning. Thanks. I'm getting 132,600. Did anybody else get that? Yeah, good. Oh, Stephanie, can you come grab one of these? All right, and then 4 letters. I think some of you guys have caught onto the pattern here. 52 times 51 times 50 times, what would the next one be? 49, thank you. All right. All right, we're getting a lot of passwords now. I'm getting 400 possible passwords. So here's the question. Which password is the best balance of safety and easy to use? And that's a question for you. So think about that for a minute. Do you want to remember 2 letters, 3 letters, or 4 letters? How secure do you want your password to be? All right, so the fundamental counting principle states that if there are P ways to do one thing and Q ways to do another thing, there are P times Q ways to do both things. So, for example, if there were 52 ways to find the first letter and 51 ways to find the second letter, you multiply them to find how many different ways you could do the 2 different letters. All right, so I promised you we were going to talk about permutations and combinations. And remember we said for permutations, the order doesn't matter. No, the order does matter, my bad. For permutations, the order matters. So Dr. Simpson has already picked out these 5 students, Amber, Brittany, Chase, Destiny, and Eduardo, to put in the first row of his class, okay? He wants to make sure that those students can focus, so he's putting them in the first row, but he's trying to figure out how to arrange them, because the order matters, okay? Permutation, order matters. All right, so let's go through this. How many students does he have? Amber, Brittany, Chase, Destiny, Eduardo? 5 students. Okay, so how many students could he put in the leftmost desk? We said 5, right? Now he's taken a student out. Maybe he took Eduardo, I don't know. All right, so after he takes one student out, how many are left for the next desk? He has 4 choices, okay? So he had 5 choices for the first desk. He took a student out, now he has 4 choices for the next one. And then, sorry, how many for the next one? Do you guys see what Nadim's doing here? Each time, it's just one less, right? Because we've already taken a student out. And then 2, and then by the time you've taken all these out, there's only 1 student left. He's gonna go on the last desk right here. All right, so let's take a minute and multiply that out. 5 times 4 times 3 times 2 times 1. Okay, so when we multiply this together, we get 120, which is interesting because there's only 5 kids, right? But it turns out there's 120 ways that he could have them arranged. Like he could have Amber, Brittany, Chase, Destiny, Eduardo, or he could keep Amber and Brittany here, but switch these other kids up and do Eduardo, Chase, and Destiny. So there are 120 different ways he could arrange those students there when the order matters. All right, raise your hand if you have ever seen this exclamation point used in a math expression before. Has anybody ever seen them in a math expression before? All right, so that's interesting, right? Because like in English class, it just means I'm surprised, but it has a very specific meaning in math. It's called factorial. So when you see that exclamation point, you don't say n, I'm surprised. You say n factorial. So the process of multiplying every counting number from 1 to n can be expressed as n factorial. So if I write 3 factorial, it means 3 times 2 times 1, which is 6. If I write 4 factorial, it means 4 times 3 times 2 times 1, which is 24. So the question is, how would we express that desk problem with a factorial? Good morning. So here's your desk problem. Thank you. Good morning. Thank you. Here's your desk problem. We're trying to express this desk problem with a factorial. So I'm going to give you a minute to see if you can figure that out. It's very short. It's going to look like one of these. All right. Wendy, can you tell me what number you put before the exclamation point? 5. Good. So if I write 5 factorial, this means the same thing as all of this. 5 times 4 times 3 times 2 times 1. Some of you guys wrote it out, and that's not wrong. Yeah, it does equal 5 times 4 times 3 times 2 times 1, but you only have to write 5 factorial. It's kind of like a shorthand to say that. All right, so one reason I wanted to show you that is because these formulas use the factorial. Let's look at the formulas. So there are 3 ways that you could solve a permutation problem. One is to use the fundamental counting principle. So if I wanted to, for example, choose 4 songs, I had 4 songs and I wanted to choose 3 to play in a specific order, I would have 4 choices for the first, 3 choices for the second, and 2 choices for the third. Another way is that there is this formula here. The formula is 4 factorial over 4 minus 3 factorial because I'm choosing 3 things from 4. Now notice the formula is going to give you the same thing. 4 factorial is 4 times 3 times 2 times 1. 4 minus 3 is 1. 1 factorial is just 1. And those 1s cancel out, right? So it gives me the same thing here. The third way is on your calculator, and this is the way that we would do it in Desmos. So I'm going to ask you, because some of you really like Desmos shortcuts, either on your phone or on your computer, open desmos.com. And we're going to solve that problem in Desmos. Now, NPR is a choice. If you go down here and you go to functions, you should be able to find the NPR, but you can also type it. You just have to type it exactly the right way. So it would be little n, big P, little r, parentheses. And what that means is I want a permutation where I'm taking r things out of n things. So I'm taking 3 things out of 4. I'm going to put the 4 first, and then the 3. And this tells me that there are 24 ways to do this on the calculator. Now notice that is the same thing you would get if I used the counting principle and I did 4 times 3 times 2. See? They work the same way. It's just up to you which one you like. All right, so you might change your mind on this, but just starting out, think about which one you like. I'm gonna poll you. Do you like the counting principle? Do you like the formula? Or do you like the calculator? All right, so permutations, the order matter. Now it's combinations and the order doesn't matter. Dr. Simpson decides to put 3 students, choosing from Amber, Brittany, Chase, Destiny, and Eduardo in the front row of his classroom. So this time he's only putting 3 students there. He has 3 desks in the front row, and it doesn't matter who goes in which desk. So, you know, he doesn't have to like separate Amber and Brittany. He doesn't have to keep them separate. They could be together. They could be separate. It might not even be Brittany. It might be Amber and Eduardo. I don't know. Okay. So how many different students could he put in the leftmost desk? So this part starts off the same as before. Okay. So we have 5 different students he could put in the left. And then how many for the next one? You already took 1 student out, so how many does he have left? 4, good. And then following that pattern, 3 for the next one. But say he picked Amber, Brittany, and Chase. Amber, Brittany, and Chase. But the order doesn't matter, right? So we want to get rid of some double counting because Amber, Brittany, and Chase is the same to him as Chase, Brittany, and Amber, or Brittany, Amber, Chase. It doesn't matter to him what order they're in. So to get rid of the double counting, we divide by the ways we could order them. So if we now have 3 people, he picked 3 of them. We're going to say he picked Amber, Brittany, Chase. We need to divide by the ways we could arrange those 3. So on the bottom here, we have 3 choices for the first one, times 2 choices for the next one, times 1 choice for the last. Now this is for combination when the order does not matter. All right, so on the top we had 60. But on the bottom we're saying because the order doesn't matter, we have to get rid of all of the double counting. So we're dividing it by 6. And it turns out there are just 10 ways he could pick 3 students out of those 5 if he doesn't care what seat they sit in. So let's look at the 3 ways to solve combinations now. The counting principle, it looks to be a mess, but if you look at it in practice, it's not such a big deal. I have 4 songs, and I'm going to choose 3 songs out of those 4, and I don't care what order they're in, okay? And so on the top would be 4 times 3 times 2, and then on the bottom, the ways to arrange them, 3 times 2 times 1. Then we have a formula with n and r and factorials, or we could do it on the calculator, and here's how we would do it on the calculator in Desmos. Okay, I'm going to try that real quick. I'm going to try, I think I'm going to try the counting principle. I could actually try them all, really, because they're going to all work the same. All right, I'm going to do the NCR first. Little n, big C, little r. And out of 4 things, I'm choosing 3. So I get that there's 4 ways. Or you can make a fraction, and on the top of the fraction, you have 4 times 3 times 2. And on the bottom, you've got 3 times 2 times 1. Also, you get 4, or you could do the formula. Fraction On the top, I need 4. What happened to my fraction there? Fraction. Four factorial. And on the bottom, I have 3 factorial times 4 minus 3 factorial. Okay, see, they all give me an answer of 4. All right, so here's the question, which one do you like? Be prepared to vote. Even if you don't like any of them, you have to pick the one that you dislike the least, okay? Are you ready? Out of these 3 methods, we're all gonna vote for the one that we like or the one we dislike the least. If you like using the, oops, I haven't shown this up here. If you like using the counting principle this time, raise your hand. Okay, I see a lot of you. If you like using the formula this time, raise your hand. Not so many. If you like using the calculator this time, raise your hand. All right, we're pretty evenly split between counting principle and calculator, and you get to pick, okay? All right, so we're gonna do some problems, and I'm gonna pause to let you guys think through these problems, but first, before we do them, let's decide if they are permutations or combinations, okay? So remember for the, where are we again? For the combination, the order doesn't matter. So let's look at 1, 2, 3, and 4. Can we find any that's a combination when the order doesn't matter? Looking at 1, 2, 3, and 4. Raise your hand if you think you found one where the order doesn't matter. All right, let's talk about this first one. When he's making a batting order for baseball, does it matter what order the people hit in? I see yeses and I see nos. Anybody here play baseball? Or softball? Nobody? Did anybody ever play baseball or softball? All right, so my son played in the Little League for a little bit, and they usually put a really good hitter up third, because if the first and the second people could get on base, then the third could hit them home. And they also put another good hitter for 4, because 4 could hit like the grand slam and hit them all home. So that was kind of important. The kids who couldn't hit at all, they were kind of at the end of the batting order. You know, they were like 9 or 10 or 11. And they did also put some good hitters at the beginning. So the order matters for the batting order. So would you call that a combination or a permutation? Look back at your notes. If the order matters, is it combination or permutation? Permutation, good. If the order matters, it's a permutation. All right. The other one where the order matters here is kind of hard to find. But the order matters if you are choosing people and the people that you choose have different jobs. Can you see one where people that you choose have different jobs? Is it 2 or 3 or 4? Number 3, good. So in number 2, you're choosing 4 people, but it doesn't say anything special about anybody. But in number 3, you are choosing 3 people, and those 3 have different jobs. And so the order matters for this one too. Permutation. So we said that the order doesn't matter for this one, so it's going to be a combination for 2. And how about 4? You're picking 3 presents from a pile of 10. Does it matter what order you pick them in? You get all the presents. Does it matter? It doesn't, no. So this is also combination. Now, we have identified them, but now I want you to find the answers. Okay, for the permutation problems, you can find the answers with the counting principle, the formula, or the calculator, your choice. For the combination problems, same thing. You can use counting principle, formula, or calculator. I'm going to give you some time, and I do want you to work with your neighbors. So talk to your neighbors as you're working. All right. For the first one, there were 9 players, and you were ordering 9 players. Are you with us? So I saw some people do that with a factorial. So you could literally just type 9 factorial into your calculator, and that would give you the answer. Some of you did 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, and that also would give you the right answer. And some of you used the calculator and you did NPR. All right, and you're choosing from 9 players and you're taking 9 players. So basically everybody is in the batting order, we're just putting them in order. So that's another way. So I'll put that last one in, but you could really put any of those in the calculator. Okay, little n, big P, little r. We're going to take 9 players out of 9 and put them in order. And this is what I got. Did you guys get the same answer? I'm going to put it on my paper first, and then I'll go back to the paper. I got 362,880. You should get the same no matter which method you used. Is there any difference between this and yours? Okay. All right. So that's your answer. Let's go down here and do another permutation problem before we do the combination. All right, so we had 22 members and we had to choose for special jobs: president, vice president, and treasurer. All right, the order matters because if I switch the order up, I've got a different person as president and treasurer. So I had 22 choices for the first, 21 for the second, and 20 for the third. Did anybody solve it that way? Raise your hand if you solved it that way. Nobody? Okay. Some of you might have used the calculator, so it would be NPR. Out of 22 people, we chose how many? 3, yeah. 3. There's president, vice president, and treasurer. That's it. So 22, 3. That's another way, right? So if you haven't done one of those methods yet, pick one to put into your Desmos. Either 22 times 21 times 20, or put in the NPR. Okay. So let's see. Take out the 9, 9, and I'm putting in 22, 3. All right, so I'm getting 9,240 ways to choose my president, vice president, and treasurer. So the other problems that we have are combinations. And because the order doesn't matter, combinations always have fewer answers. We're not going to get so many. So let's go to problem 2 on the top. Okay. I think a couple people solved this with the counting principle. Raise your hand if you use the counting principle to solve this problem. I know Sarah did. Anybody else? Okay, raise your hand if you use Desmos to solve the problem. Okay, if you use Desmos. So I'm going to show you the counting principle just because some people liked that. So we had to choose 4. So we would have 20 times 19 times 18 times 17. But remember, we divide it. All right, and the ways that we can arrange those 4 numbers, there are 4 choices for arranging the first, 3 for arranging the second, 2, and then 1. So that's one way to solve the problem. Or if you did an NCR, out of how many people? How many were all together? Out of 20 people, we're choosing how many? We're choosing 4 out of 20, right? All right, so put one of those into your calculator. We should get the same answer regardless of which one we pick. Did anybody use the formula with the factorials? That one works too. All right, let's see. Okay, I'm getting 4,845. Can anybody confirm that? Got that? Okay. 4,800. You got it? 45. Mm-hmm. Good job. Okay. One last problem, and then we're going to do a Kahoot to review this. A person can select 3 presents from a pile of 10. How many ways can this be done? So you can still use your counting principle, or you can use the calculator, but I saw more of you using the calculator, so I'm going to put that here. What number do I put first? 10. Good. It's the number that you're picking from. And then I put comma, what number? Is she right? Yeah. Okay. So put that in Desmos. We'll get our last answer. And then I'm going to have you keep your notes so that you'll have those for next class. And we'll get an answer. Okay, so I'm getting 120. Oops.